Good morning. Okay, let's try to finish the complex number today. Okay, so let's get started. Okay, so complex number, basically, according to our notation, it's A plus JB or A plus IB. Okay, and A here is called the real part, and B here is called the imaginary part. The notation I or J, they are essentially the square roots, -1. Okay. To describe a complex number in complex plane, so we draw a real axis, we draw an imaginary axis, and then you find the corresponding component, the real part and then the imaginary part, and then figure out this location of this complex number. It's like drawing a vector. Now, in the last lecture, we also introduced two concepts. So we can have a theta angle, which is the angle between the horizontal axis and this line segments of representing this complex number, right? And we can also have a magnitude representing this magnitude of the line segment of this complex number here. So this magnitude here, okay, we can call the absolute value of z. So now we can just introduce just a slightly different concept. We call that polar. So polar form of complex number z. What does that mean basically? Actually, it's the same idea. Basically, still use theta, and we're going to call this absolute value of z, call it equal to r. Okay, equal to r here. So if you recall that the polar coordinates, what's polar coordinate? The polar coordinate is x equal to r cos theta, y equal to r sine theta. That's polar coordinates, right? R and theta is the polar coordinates. So in this case here, we introduced r and theta here. Okay, yeah. So now it's basically like in Cartesian coordinates. Then this a over here. So it is equal to r cosine theta. Sine theta. Right, so that's polar coordinates here. And what is r? R is absolute value of z and square root a squared plus b squared. So that's r here. Okay. Yeah. And what's the theta? Theta is angle. Same definition. We call it the argument, right? In the previous lecture. So theta is angle from the horizontal. It's always from the horizontal. Okay. And if you go counterclockwise, it's always positive. If you go counterclockwise, it's negative. So in this case, our theta basically is tan inverse E over A. However, in the last lecture, in the example I gave you, you cannot fully trust the calculator, the value they given to you by the calculator, right? You need to look at the actual location of this complex number to figure out the actual theta value, right? Yeah. So this way, you can figure out what's right? So if I don't want to express z in terms of a and b, my z can be expressed as a plus 2b, so a plus 2b can become a is r cosine theta, and b is r sine theta. So you have a slightly different way of expressing this complex number using r and theta now. So you can take out this r right here, which is cos theta plus j sine theta. So giving you a complex number, okay, you should be able to figure out the corresponding r and theta, and you will be able to have this kind of writing at here. All right? Yeah. So what's the advantage of the polar form? We'll talk about the advantage after the next topic, which is the Euler's formula. All right. So bear in mind, we have some advantages over here. Okay. What are the advantages here? Okay. Yeah. So essentially, why don't you stay with this one? Why do you want to use r and theta? Right. Yeah, so there must be something good over there. Okay, so that's the first thing that we're going to talk about today, the polar form. Any questions? Good. Okay. So second one here is let's look at exponential plus. So this is something new at here now. Okay, so e to the power z, basically, my z is a. Let's say z is this. Okay, so z is x plus 0. Z is complex number. Okay, this is quite different because before this one here, so always z is always e to the power, always e to the power something real, right? Yeah, and then if you grow at the real number, e to the power 3, e to the power of 5, right? But now, e to the power of a complex number, okay? So what exactly does that represent? Okay? Is that still going to be some sort of a growth, okay? So, but before we move on, let's write down a formula first, okay? So z is defined as this, so z must be this down here, okay? And we'll know that e to the power a plus b, which is what? Right? It's this, okay? So this must be this. And this is nothing new. This is e to the power of a real number, so we'll just leave it as it is, right? It's basically this portion in here, right? This portion. So what exactly this portion here? So this is the formula I'm using here, okay? So we're going to stay as e to the power of jy, which is cosine y plus j sine y. Okay, so this is new here. Now this one here is actually so-called Euler's formula. Okay, so basically you can either call this whole portion or just this small portion over here. Okay, this is called Euler's formula. Yeah, this name Euler, you see that so many different places, right? Okay, so let me single out this thing here. Okay, gy equal to this. Single this out here. And then we'll look at it, the meaning of these things here. Okay, so first of all, what's the proof? How do I prove this guy equal to this? Let's state the proof here. So the proof is you need to use Taylor series. Basically, use Taylor series to expand this term in here. Taylor series. You take this gy as if it's one single quantity, and then you use Taylor series to to expand this thing here, and we'll be able to choose this number. Use Taylor series expansion on EJY. Yeah, so the whole idea is basically Taylor series expansion of this e to the power of u is 1 plus u squared 2 factorial u cubed 3 factorial like this. Okay, like this. This is a regular Taylor series expansion on a standard format of e to the power something, right? So now my u is gy. If you plug this into here, okay, so we're going to be able to derive this one here, okay? And we're going to have to use Taylor series expansion on the cosine y and sine y. However, okay, what I need you to remember is this guy here, or this guy. It doesn't matter. Okay, so just write down a few times. You'll be able to remember what the Euler's formula is, right? Okay, yeah. Okay, so this is a Euler's formula, right? And before we move on to talk a little bit more about the Euler's formula, let's go back to this polar format here, okay? Let's go back to the polar format. So now you look. If I look at the polar format I just introduced it here. I said given a complex number, you can rewrite your complex number as r cosine theta plus g sine theta, right? Okay. So now when you look at this portion here, look at this portion, right? This portion, cosine theta plus g sine theta. Now what's this guy here? This is basically some term plus another term, right? And if I look at my Euler's formula here, look at that. That's cosine y plus sine y, right? G sine y. So if I change this y here to theta, that means this portion right here just basically what? E to the power of a j theta, right? E to the power of j theta. So in other words, right? So in other words, okay, yes, right? In other words, my red, which is written on this one here, it can be written, okay, according to the Euler's formula, it can be written as Rej theta. Okay? So this is according to the Euler. Right? According to Euler. Any question right here? Okay? Yeah. Okay? So now you can see now, okay, given a complex number, how many different formats I can write this complex number as? First, a plus b, right? The second, this r cos theta plus g r sine theta. And third is r e j theta. Does that make sense? Right? So this all three things represent the same complex number. As a matter of fact, there's a fourth more format, and we're going to call it, and just we're going to introduce, we're going to use this r angle theta. Okay, r angle theta. So in the AC circuit analysis, okay, and when you use so-called phasor analysis, which I'll talk about shortly, okay, and this is what we're going to call a theta here, called a phase. It's called a phasor here. Okay? So all of these 1, 2, 3, 4, they all actually represent the same kind of complex number right here. All right? Yeah. Okay. So now let's talk about what's the advantage of polar form. Okay, advantage here. Right. Remember the question mark. So advantage of polar form largely depends on this actually Euler's format here. Okay, Euler's formula. Now, if you remember, when we do multiplication or division, so when we have a z1 multiplied by z2, or z1 divided by z2, what the standard operation is, you basically plug in this a1 plus ab1 and a1 plus a2 plus jb2, right? And then you do this regular multiplication, right? And same thing here, this will be a1 jb1 over a1 a2 plus jb2. So standard operation. So this one here, how do you operate? You have to convert this denominator using the conjugate, the concept, right, to get a real number part, and then simplify this whole thing into one simplified complex number here, right? Yeah. So you need a little bit calculation here, right? Yeah. Now the other way is, now we learned this Euler. The other way is this. Let's say if I use this for example, huh? Yeah. So when you calculate the division, what you can do is, you see the top one here is complex number. If I want to convert this complex number using Euler's formula, so basically I need to find what? The magnitude, right? And I need to find the corresponding theta, right? But anyway, I should be able to find the magnitude R1 for this complex number. Again, I can find an angle, or so-called phase, for this complex number. Does it make sense, right? Yeah. And same thing for the bottom one here, and I should be able to find the corresponding R2 and theta 2. Okay? Yeah. So now, the division, right, that here becomes this divided by this. Well, this divided by this, how do I carry this out? That's simple, because R1 divided by R2, right? This is just one real number, two real number division. And this division right here, this is division of two exponential numbers, which is e to the power of a divided by e to the power of b, and it equals to e to the power of what? A minus b, right? Yeah. So this is basically e to the power of j, this minus this. So I can take the j out, which is theta 1 minus theta 2. Okay? Yeah. So now you see, when after I converted this one into this polar format, or this and then using this Euler's formula, instead of doing the regular multiplications, divisions, right? This is multiplications here. This you need lots of regular multiplication divisions. And now what I did here is what? This is subtraction, right? It's subtraction. So you turn those divisions and multiplications into subtractions. So that's an advantage. I guess nobody wants to do, well, not nobody, but I guess you would prefer subtraction additions with, from this multiplication and divisions, right? Yeah. So that's basically the advantage here, right? This is subtraction. And over here is multiplication or division. Okay, or division. As a matter of fact, this is a similar idea when you learn log here. When you learn log. So log AB, right? Originally, if you have A multiplied by B, then you take a log. Then instead of carrying out this multiplication, it becomes what? Right? Yeah, it becomes addition, right? So sometimes, right, you probably would think, why would you do that? Well, sometimes when you do this conversion or transformation, it does save you some computation. It actually basically gives you a different perspective of computation, okay? And you will see that it makes things clear. Okay, so that's an advantage of this thing here, okay? Yeah. Okay, so now let's get back to the Euler's formula, okay? Y plus j sine y. Okay, yeah, so let's see the formula here. Now let's take a better look at this thing here. Okay, let's see what exactly is going on here. Okay, yeah. Okay. Now before we move on to let's look at this example. Now instead of calling y here, okay, I'm gonna give it a different quantity. I'll say this is e to the power of j omega t. Right? So I'm basically letting y equal to omega t here. So technically speaking, according to the Euler's formula, I should get, I should get this guy here, right? Get this. Okay, so now let's see, what does e to the power of omega t give you? If that's what will be this graph of e to the power of omega t? It's going, right? Omega, let's say omega is a positive number. It's basically going to quickly, right? So exponentially growing, essentially, right? Now, this is e to the power of g omega t. Technically, it is also e to the power of something, right? But the question is this also going to be growing exponentially like this side here? Right? Well, the answer is actually no, because when you look at this side here, that doesn't look like it's growing exponentially here, right? So then the whole thing is, what does this mean? What does it, if it doesn't grow exponentially, then how does it change as it, because here t changes to infinite, the value goes to infinite, right? The value goes to infinite. How about this guy here? As t goes to, as basically as you changing t here, as t goes from 0 to somewhere, then how does this guy change essentially? Yeah. So what we do is we look at it from a real and imaginary, the complex plane at here, okay? Complex plane. Let's look at how this complex number changes as t changes. Okay? So as t changes, so how does t changes? What does this guy change? So it's actually quite simple here. If you look at this one here, look at this. This is e j omega t. What this one is, right? We can prove that using Taylor series. So what's this real part? The real part is cosine omega t, and imaginary part is sine omega t, right? So omega t, if you think of omega t as an angle here, basically, let's say if I draw any line here, and this, if I say this is omega t, does it make sense? That makes sense, right? So when you change your t starting from 0, where is omega t? Is here, right? It's here. And as the t changes, basically this angle just rotates at here, right? This angle rotates here. So then cosine omega t, if you think yourself, there is a unit circle here, basically with a radius of 1, then at anywhere on that unit circle, okay, and anywhere on that unit circle, okay, what's the coordinates of that, or basically we're not calling coordinate, but let's just think of the coordinate. What's the coordinates of this point in here? Coordinates basically means the x component and the y components here, right? So x component, this part is 1, what? Cosine omega t. And y, this is 1 multiplied by sine omega t. So essentially, right, this point in here representing this complex number, right? This point here, that's cosine omega t plus j sine omega t, which is ej omega t. Okay, ej omega t. So now it's kind of clear now, right? That's kind of clear. So how does ej omega t changes as t changes? It's basically going around the circle, right? It's basically going around the circle here. So as t changes, it doesn't grow exponentially anymore. Because of this complex number j over here, this e to the power of g omega t, or this e to the power complex number here, essentially it's going around the circle. Okay, it's going around the circle here. Is that clear? Yeah. So you can think of this. You can think of this ej omega t over here. So this guy here, this is essentially sort of a rotating. You think of this as a vector here. You can think of it as a rotating vector, right? With angular speed of omega. Okay, of omega. Now this ej omega t, if you're gonna go to electrical program or if you're gonna do some signal processing, you're gonna say this quite a lot frequently, right? Yeah. This basically omega here oftentimes representing the frequency component in the signal. Okay. In later part of this course, we're going to talk about Fourier transform and also in Laplace transform. We're going to come back here to this formula. Right? So bear in mind this this Euler's formula, e over t, what does it represent? Does it represent a point moving along a circle? Okay, moving around a circle here. Okay, so now let me give you some small exercise over here. So let's take a look. Now we learn Euler's formula. Okay. What is e to the power of j? It's a simple one. What is e to the power of j then? And what is 3 to the power of j? And what is instead of 20, let's call j. What's j to the power of j? Starting with a simple one here. What's e to the power of j? Yeah, close to what? Close to 0? E to the power of j means y equal to 1, right? Okay, so you can use your calculator to figure all this out. Well, if I want to use my circle over here, where is cosine 1 plus 2 sine 1 meaning 1 readings, right? 1 reading is 57, right? 57 something degree, right? So it's somewhere over here, right? Somewhere here. Okay? Yeah, so that's this one here. How about this guy here? So 3 to the power of j here. So in this case here, you need to think everything in terms of this exponential. Actually, as a matter of fact, you only say exponential, right? Exponential function or exponential function. When you say exponential, you don't think, oh, the base is e. Actually, this is also called exponential. It's also exponential. So what you can do is the 3 right here, right, equal to what? E to the power of ln 3. Is that it? Yeah. So then 3 to the power of j will be, that makes sense, right? Yeah. So then this thing here, e to the power a to the power of b, which is e to the power of a multiplied by b, right? So which is e to the power ln 3j. And then according to Euler's formula, what is this equal to? Cos ln 3 plus j sine ln 3. So you can use calculator to calculate this, what this guy is. Okay? So this 3 to the power of j, it's also a point on the unit circle over there, right? Okay. So how about this guy here? 3 to the power of j. So the question here, what does this complex number g equal to? Right? G equal to. So now if I still use my complex, this plane here, right? Where is that g? Where is it? Is it here? Or is it here? Is it there, right? If it's here, how do I express the g using this formula here? E to the power of g what? When you're here, what's the value of omega t? Pi over 2. That's right. See, right? So from here to here, that's omega t. So that's pi over 2. So that means this g is e to the power of g over 2. Any questions here? Yeah. What's your question? Well, you see, I said this is a point on the circle here, right? Do you agree this is a point where G is? Yeah. And this point here, remember this definition is representing all the points on the circle as t changes. So omega t is here representing the angle, right? Representing the angle from here, horizontal axis, to where you are. So where you are, you're here. So what's the angle from here to there? Yeah, pi over 2, right? So this is y ej pi over 2. Now if you don't carry this out, Huh? Right? So what's a cosine pi over 2? 0. What's sine pi over 2? There it goes. That's it, right? That's good. Okay? Yeah. Okay. So now this j to the power j will simply ej pi over 2 to the power j. And that's j pi over 2 multiplied by j. And what's this guy give? What does this guy give you? Exactly. So amazingly, this j to the power j give you back a real number here, right? Give back a real number, right? Yeah. So I think we can find this. What's j to the power j to the power j? Right? Yeah, that's right. So just this guy to the power j, so e negative pi over 2j, right? So, okay. And what does e to the power negative e to the power negative pi over 2j? Excellent. Okay. And how about this guy? Cosine negative pi over 2 would be 0, right? And this guy would be no negative 1. So negative. Okay. Yeah. All right. So now you learn complex number, and whenever you see an exponential format, basically something to the power of something, right? Whenever you see something to the power of something, you can always use this technique here to transform it into this into the concept of the circle, right? Yeah. Yeah. No. So j to the power of j is this, right? Oh, j multiplied j is negative 1. So that's why this is negative pi over 2. J multiplied by j. Is that good? Yeah. Okay, so now let's move on. Okay. Now let's look at this Fisher representation. Okay? So Fisher representation of a sinusoidal signal. Okay, so where this is, what's the most application of this one here is this. Let's say we have RC circuit. And then you're giving the circuit the sinusoidal input. Let's say we call this V as sinusoidal input. Maybe this A cosine. Okay, that's the sinusoidal input. And then you're interested in what's the output at this capacitor at this location here. Okay. Okay. So now the whole thing here is you might think it is actually easy because well, let's just apply this KVL law. This guy divided by this thing. Divided and multiplied by something, right? So. But actually, it turned out it's not as easy as the DC circuit as it is, right? Yeah. So in this case here, yeah. So often in time, and this is an application where the so-called Fisher representation of sinusoidal signal. So we don't want to calculate with this guy as originally whatever it is. We're going to transform this one here into this so-called Fisher representation, right? So let's see what does that mean. So let's go back to our complex number. So if you remember, I said when I have a complex number, I can write the complex number using this exponential format. Or now I introduce another one here. Just call it R angle theta. Okay? So they all refer to the same thing. Okay? The same thing. Okay, so now how about this sinusoidal one here? Right? So now let's say call this VT HA cosine omega t plus phi. So we're going to do some manipulations over here. Okay, we'll do some manipulations, and instead of using this one, to write it using complex numbers. So A cosine this one here. So I'll just write it down here. This A cosine here will equal to real part A ej omega t plus phi. Okay, let's say you can see these two here. Okay, so this A cosine is equivalently to say that's the real part of this complex number. Does that make sense? Yeah, right? So why is that? What's this complex number? This is cosine omega phi plus j sine omega t plus phi, right? And the real part is basically this part. Okay? Yeah. And inside this big bracket, okay, this is ej omega t plus phi here, and that's equivalent to say ej phi ej omega t. Okay. Yeah. Okay, so we separating this the phi and omega t out, right? Now, looking into this big bracket here, inside this one here, ae to the power of j phi. This guy here is basically called phasor. This guy is called phasor for this VT signal here, okay, the VT signal. All right, yeah. So it doesn't make any sense yet, but you'll see the advantage, okay? Yeah, so this is kind of called phasor. So it's actually quite simple now. Basically, if you have a sinusoidal signal, and all you need to do is just take this. This is a phase, right? Why is it called phasor? This is called a phase, right? Yeah. So actually, it's not called phase. So is it called phase? Yeah. So then all you need to do is AEG phi. That's basically called phasor. Okay. Alright, so if I relate that to the circle things here, if I relate that to the circle things, okay, EG phi, if I just simply look at this AEG phi here, so originally that was a unit circle, but now if you have a constant number A is here, basically now the circle has, instead of a radius of 1, so the circle will have a radius of what? A, right? It will have a radius A. So then EG A multiplied by EG phi, that essentially representing is a complex number, okay, somewhere over here with an angle between the horizontal axis and that complex number, which is here, is phi here, right? That's phi. Phi is always, angle is always defined from the horizontal axis to the location of where it is. Okay, so this is AEG phi. Okay. So how about this guy here? How about this AEG phi EJ omega t? Right, EEG phi. So this is where this is. And then if you multiply by another EJ omega t, then basically it's like this. You're gonna starting from this location, then rotate by another quantity of how much? Omega t, right? So by another quantity omega t. So this is omega t at here. Then you end up over here. So this is AEJ phi EJ omega t. Right. Okay. So that's what it is. Yeah. No, in this case here, this omega t here is going to be starting from this location based on this question. Yeah. If I just only look at this one here, right? You want to say where is the EG omega t? Then yes, you're starting from horizontal axis, and you find out where this EG omega t. All right. Yeah. But I'm looking for this location. That's why I started from this initial position here up to here. Okay, so basically, actually go back to this one here. You can always think of this e to the power g omega t as sort of a rotating factor. Whenever you multiply this e g omega t to something else, right? So all it does is it's going to rotate that by an angle of omega t, okay? By a further angle of omega t. Okay, so now let's take an example here. Okay, so how do I deal with this facial concept? How do I simplify this size? Make use of it. So let's take an example here. So one example here is let c equal to 3 cosine 20t plus 10 degree minus 5 cosine 20t minus 30 degree. All right. So I want to simplify this one here. I want to simplify this. So basically, there are two cosine functions with different amplitude, but same frequency at here. Okay, but different phase, right? Different phase. That's the common part. As a matter of fact, if I go back to the circuit here, as you know that this is actually a so-called linear circuit, right? In 246, we have the differential equation for this one here, right? RC circuit. This is the linear circuit. This is if R and C values are not changing. So this is actually going to be an LTI system. Okay, LTI system. So for LTI system, when you inject this LTI system with a certain signal of a certain frequency, right? At anywhere on that system, for example, you're interested in output of this capacitor, and the output of the capacitor will have the same frequency output, okay? But maybe different phase and different amplitude. So the VC, as you can see that, it's probably going to be cosine omega t plus another phase at here, okay? Yeah. Because this is the RC circuit is a linear first order ODE, right? dVc over dt plus 1 over RC VC equal to 1 over RC VS. Because R and C, we consider them a constant, so there's no time varying parameters. So that's why I call it an LTI system. Right? Yeah. So this is actually important for any linear system. For any linear system, when you inject the linear system with certain sinusoidal frequency into it, what's coming out of the linear system, time varying system, what's coming out of there? It's another sinusoidal signal, but with a different amplitude and different phase, right? Different phase. Yeah. Okay, so this is basically similar two frequencies, same frequency adding together, right? So what we want to do is we want to simplify this into this format here, okay? Into this format. So basically, we want to get here. Is that okay? Yeah. So there are different ways of doing this one here. If we never learned this complex number phasor, you can also do that using this trig identity, right? So in the tutorial, I'll show you some ways of doing this. But now let's make use of the phasor concept to do this simplification here, right? Yeah. Okay, so here's what we're going to do. Okay, this is this guy minus that guy there. So I'm going to start with equal signs. Okay, right? Okay. So this one here, I'm sorry, this is the real part. So it's 3 e to the power j 22 degree. Alright? Yeah. And this part here, we call it, this is a negative real part, slide e to the power j 22 minus 30 degree. Okay? So when you have a real part of this minus the real part of that, okay, and that's equivalent to say this is the real part, 3ej20t plus 10 degree minus. So just basically put everything into one big bracket. Okay, so just put everything into one big bracket, right? That's the same thing. So it's like there's a real RE thing here as well. So like it's a linear operator, right? Remember that it's a digit property, right? A digit over here. Okay, so then we're gonna basically separate, okay, the two terms here just slightly. The first one is EJ 10 degree, right? And the EJ 20. Second one here is 5 EJ 30 degree, and EJ 22. Yeah. Okay. So I got a common factor EJ22 for both terms here. So I'm going to take this common factor out, and so that gives me what? That'll give me this guy here. This, right? Yeah. Here? Here? Oh, negative 30, right? So it should be negative 30, sorry. Good point. Okay, negative 30, negative 30. Okay? Alright, so now, if I look into this term here, I look at this term here. Do I have everything? I 10 degree, right? And negative 30 degree. So basically, what this one is, and this is also e to the power of a certain constant here. So, technically speaking, my 3, this one here, these terms here, I can calculate it. I can calculate. This is essentially a complex number. And we learned the unit formula. What's the first? If I apply the unit formula for the first one, what's that? That's E3 multiplied by what? Cosine 10 J sine 10, right? The second one is 5 cosine negative 30 plus J 5 sine negative 30. Does that make sense, right? Yeah. So that's this one. Now you bring out the calculator and you calculate this thing here. And this is this one here is you do need a calculator, okay, a lot of time, yeah. So calculate this each one a quantity. This is just basically addition, subtractions of complex numbers here, right? Addition, subtract complex numbers. So if you carry this out, this should give you negative 1.37572 plus J 3.02094. Okay, you should get this guy here. Okay? Yeah. Yeah, when you do this calculation, make sure you set your calculator to degree, right? Yeah, because this happens quite a bit. Sometimes when you use a reading, cosine 10 reading is very different from cosine 10 degree. Alright, so now I got this guy is a complex number, but I don't think it helps that much here. So now what I'm going to do is, I'm going to convert this back into this format. Okay, I'm going to convert this back into this format. So which means, for this particular one, what is my R, what is my theta, right? So R is what? Square root, square of this, plus square of that. And that's approximately this way. And theta, right, theta is arc10 B over A. B is this, A is that. But you need to look at where is A, where is B, right? Where is A, where is B? Where is this complex number? This complex number is in which quadrant? It's somewhere here, right? Somewhere here. So your theta angle is actually going to be 100 something degree. So your calculator, you should plus 180 degree when you use the calculator, okay? So this should be 100 of this, okay? 100 of this. So then, if I go back over here, okay, this is the real part, okay, R 3.32. Take that, EJ 114.5 degrees. Then EJ 22. You see that, right? So there are two exponential things multiply each other, so that basically is equivalent to e to the power of this guy plus that guy. So I'll write it down here now. So the real part, 3.32 e to the power j omega t plus 114.5 degrees. Right? And what is the real part of this one here? That's basically what? 3.32 what? Cosine omega t plus 114.5 degrees. See, now I get what I want, right? I get a cosine omega t plus 5. Now, can you see the logic in here, right? Yeah, this is a little bit twisting, but because you're going from this real domain to complex, and then after going through some steps here, I end up with this. All right? Yeah. Any questions? Okay.